typically in RRH, if I draw the block diagram of RRH, typically we'll have 4 ports. It will be mentioned as ANT0, ANT1, ANT2 and ANT3. Similarly, in antenna also, the same thing will be mentioned. ANT1, sorry, 0, 1, 2, 3. Mainly it will be mentioned as plus 45 and minus 45 degree. So you just need to do the connection, and RRH will also have other ports like power port here, SIPRI port here, and let's say RET port here. And there are some other vendor specific ports also available for their tuning purpose. So these are the typical ports what you find in any vendor. The antenna port, depending on how many antennas it support. And mind you, we have come up with something called 64T, 64R antennas also. In this configuration, we don't see antenna and RRH being separated. What they do is they integrate RRH with antenna, and this is usually called as massive MIMO unit. And since we cannot have 64 jumper cables, they integrate RRH with antenna, and typically it will be only SIPRI cable here. So okay, we see these products also. Okay. But now, as a predominantly used one, the structure is this only: the RRH antenna and the BBU, where RRH for each sort of port, we have each separate port for each antenna.
Clear, thank you.
Okay. Any other questions or comments? Okay, so let me
finish.
Yeah.
Hello. Yeah, I have one query. So
yeah.
Actually, supposedly, if you have two different band RRH, correct? Okay, 2x2 band, 2x2 MIMO, two RRH you have. Okay. Now you want to connect the same with the particular one antenna, which has four port. It will be operational or how?
Can you repeat? So what you are saying is,
supposedly you have two different bands of RRH.
Okay,
2300 maybe, and another one is 8.
Okay.
Okay. Now you want to connect to particular one antenna, just one antenna, not dedicated to one RRH to one antenna, another RRH to another one antenna. You will have only one antenna.
Okay, you are telling about single band antenna.
Single band antenna, yes.
Okay, so this is 1800 separate antenna, this is 2300 separate antenna. Okay.
Yes. No, now this what we did here, we have to replace this 2300 and 100 different antenna to a particular one antenna. Is this possible? Is there any product available?
Yes, this is all available, right? So basically, this was done in Geo also initially. What they had done is they had this separate RRH and separate antenna. Okay, this is called single band antenna. Okay. Now what they did was they purchased something called multi-band antenna. So multi-band antenna supports 2300 and 1800 in same antenna. So what they do, they dismantle this antenna, and they connect both the sort of RRH to single antenna of multi-band. These things are all possible nowadays. So we have a single band antenna, we have multi-band antenna, we have penta-band antenna.
The ராஜேஸ்வரின்றவங்க இன்னும் வச்சிருக்காங்க. திரும்ப ரிப்ளை
anyone
team list வந்து PDF மாதிரி அனுப்பிச்சிருக்காங்க.
It is fine. I got it.
Somnath, you got my point?
Yeah, I got it.
Okay. Any other questions or comments? Okay. So let me move to the day 4. Day 4, we are talking about some of the parameters inside LTE. This might be more so required on the RF side, wherever we are, let's say, doing the drive test, the RF planning. So that's one point we are discussing, and we are also discussing on the cell states, the mobility, what we call it as idle mode mobility, the handover. These are the things we are going to discuss in our today's session. So let me start. So this is what's in store for us with respect to day 4. We'll look at what are these things, what is RSRP, RSRQ, RSSI, SINR. I think most of the things you might have seen in your call logs, block BLER, typically we call it as blur. Then what is SINR? I think CQI mapping in LTE with respect to this SINR, we'll discuss that. Then we already saw what is PCI. We just revisit what this PCI means. The next topic is, this is more so related to the RF side. Okay, this is more so related on the RF side. We'll look at some of the UE states, how it is sort of different with 3G. If you already have some background on 3G and 2G, you'll see that UE state is very simplified when compared to what complications are they are done in 3G. So we'll look at those differences. And also we will look at what this EMM bearer connection is and the signaling connection. Okay. And the last topic will culminate it with something called as handover, which is very important. How the handover takes place. What do we call this handover as? Typically, we call this as, in LTE, we call this as hard handover. In 3G, it was called as soft handover. And in 2G, it was typically called as hard handover. So how this hard handover takes place, we have something called as event-based handover here. So what does this event-based means? How is it different from what we had it in 2G? We'll discuss all these things when it comes to handover. Okay. Now, let me go to the first topic. So this is nothing but RSRP. So RSRP, see these concepts are purely on the LTE side, because earlier in 2G or 3G we had only the total power being calculated, which we used to call it as RSSI, received signal strength indicator. Okay. Now we have got away with this particular thing. This is very important. This is called reference signal received power. So what this reference signal mean? I'll just go back to our day 2 session so that you will understand what this reference signal means. Just a second. So I'll just share my day 2 presentation so that you can understand things. I hope you are able to see my screen now again. Yes. So yeah, thank you. So you can see here reference signal. We are looking at this reference signal and looking at the received power. What does this reference signal mean? The reference signal here is the average power of one single antenna, and as we discussed, this reference signal will be there in frequency domain having a 6 subcarrier difference. In time domain, it will be 4 OFDM symbols difference. So this will be a reference signal for one antenna. Okay, one antenna. So similarly, if I have multiple antennas, see, if I have one more antenna, there will be one more antenna which they have represented with R1. Okay, you can see here R1, R1. Similarly, if we have 4 antennas, see, basically this is 4. So if you have 4 antennas, you can see rest all R2, R3. So if you have these antennas and these signal, this is the signal what you will measure, and we call this as RSRP. Okay, RSRP. So RSRP if we have 4 antennas, there will be 4 RSRP value. We will simply restrict ourselves to single antenna now, so that we can understand things better. So single antenna, I am coming to this. So now you understand what do you mean by RS first. So this is reference signal. The reference signal received power is the one which we are discussing. Okay. So I'll go back to whatever we are there with day 4. Okay. Now this RSRP, why this RSRP is used? For the simple reason that whenever you are latching onto the network, okay, the first thing you will measure is RSRP. Why this is required? Basically, if you want to do a cell selection, that is the first thing what we do. Then we do something called cell reselection. Okay. And also for our handover measurement. All these things we require this important parameter that is called as RSRP. Now, just to revisit what this cell selection reselection means. See, let's say we have an e-node B here. There is a mobile which has just powered on. So once it is powered on, it will go into something called idle mode. Okay. Once it goes into idle mode, if I move from one e-node B to the neighboring e-node B in idle mode, this is called as cell reselection. Okay, cell reselection. So whenever you are doing a mobility from one e-node B to another e-node B, this is called as cell reselection, and this usually happens in idle mode. And for this, the authority is given to the mobile itself. Mobile can do the cell reselection and cell selection based on its own sort of configuration. Okay, the information will be provided by e-node B on what basis you should do cell selection and reselection. Basically, we get into something called as, I am just alluding to this topic, which is called SIB3 information. SIB is called system information block. So I'll come to what is SIB whenever we are going for channel mapping. Just understand this, that whenever you are getting into idle mode, all the information will be flown into e-node B, that at what time you should do cell selection and reselection. And e-node B, based on the signal strength of RSRP, it will do the cell selection and reselection. Okay. So this authority is completely given to the mobile, and mobile can do reselection and cell selection based on the RSRP signal strength. Now, what do you mean by handover? Okay, what do you mean by handover? Whenever a mobile goes in something called as connected state. Okay, connected state. Connected state means what? If you are doing a, let's say, a VoLTE call or a video call through an operator like Jio. So what we do, let's say you are changing this particular e-node B. That means from your source e-node B, you are going to some neighboring e-node B here. Okay. For this also, we do the RSRP measurement. Okay. The RSRP measurement is done, first thing. Second thing is, to do this handover, the e-node B will know this RSRP value, but the authority of doing this handover is given to the e-node B. So this is very important. This is the difference between cell selection and reselection and the handover. It might look same. First thing is, this happens in idle mode, this happens in connected state. And the second part is, here cell selection and reselection will be taken care by UE only, whereas here the handover is taken care by not the mobile, it will be taken care by e-node B, but it will be assisted by the mobile. Mobile will give some recommendation telling that yes, my signal strengths are reducing. Let's say I am here, my signal strength are reducing. It will send in uplink direction telling that my RSRP value is very low. Please allow me to do handover. But it is up to e-node B to actually do the handover. So the authority is with e-node B, but assistance is given by the U. Okay. So that's the difference between cell selection, reselection, which is in idle mode, and handover, which is done in connected mode. And this sort of handover we call it as hard handover. Okay. Now, so I hope you understood what do you mean by the cell selection, reselection, and handover. For all this, we require this RSRP value. Now, what is the typical RSRP value? The RSRP is always measured in dBm, decibel, milli, and the range is from -44 to -140. -44 means it's a very good power level. -140 means I am in poor RF condition. That's what it means. Okay. So typically you can see here where all it is applicable. They have mentioned here about all the frequency, intra-frequency, inter-frequency, connected mode. Okay, connected mode, intra-frequency, connected mode, inter-frequency. Okay. I hope you understand what do you mean by intra and inter. In case if you have any questions, please ask me, or else I'll just go through the next topic. Right. So you can see here RSRP is defined as linear average over the power contribution of the resource element that carries cell-specific reference signal. Okay, reference signal within the considered measurement of the frequency band. Okay. So cell-specific reference signal R0 means typically will be used for the single antenna. If it is R1, that means we have one more antenna which is being decoded by the mobile. So this is the second antenna what we have. Fine. Any questions or comments before I move to the next slide? Okay, so you can see here, this is one more important thing. Whenever you look at the call logs, let's say you go for a drive test and look at the call logs, you definitely, or sometimes, I think nowadays you get this value only, either somewhere around, we typically don't get -40. We typically start somewhere around -70 to somewhere around -90, or let's say -60 to -90. Typically, this is the range what we get in our drive test. But 3GPP specification says that for each and every RSRP value, there is a corresponding non-negative integer value. So, for example, let's say -40 will be sort of notified as 0. So remember this: if it is -40, mobile will, let's say, put it as 0. The E-node will clearly understand that it is -140. So similarly, for each and every RSRP value, there is a corresponding non-negative integer value which is being there. So the range is from 0 to 97. Okay. So -140 is 0. Okay. And -44 dBm is 97. Okay. So just for some better management purpose, they have given certain values. And remember this: the unit used here is dBm, decibel per millivolt. Okay, 1 millivolt. So very important thing is RSRP is a signal strength and indicative of the cell coverage. Okay. So the link budgeting is purely based on these certain aspects what we discussed. I hope everyone are familiar. I just want to tell you how the link budget is typically done, so that usually I'm looking at certain assumptions, some preliminary assumptions, and doing some link budget. Link budget it is nothing but to budget how much uplink and downlink sort of estimation we get in a certain area to do the coverage and capacity planning for LTE. So let's say this is E-node B. Okay. Typically an antenna, so you can see here the antenna here. Antenna will have a gain. Okay. The gain of this antenna will always be in something called dBi, decibel, with respect to the isotropic antenna. Typically what we see is this will have a gain because this will be a directional antenna. This is not an omnidirectional antenna, this is directional antenna. Typically what I see is somewhere around 16 to 19 dBi. So for simplicity purpose, let's say I have 17 dBi antenna. Let's say this particular E node B or the BBU or the power what we have provided is, let's say 20 watt. Okay, typically we get 20 watt or 40 watt, all these things. So let's say 20 watt. 20 watt becomes 43 dBm. Okay, 43 dBm. So the 43 dBm is fed to this antenna. Okay, so 43 dBm, I am not considering, see, I am not considering the loss which is being incurred by this jumper cable. Always a cable will have a loss. So let me ignore this for simplicity purpose. So let's say 43 dBm I am putting across in the antenna. Antenna has a gain of 17 dBi. So totally it will be 60 dBm as my effective isotopic radiated power. Whenever we are talking about antenna will radiate a power, and that power we call it as EIRP. If you remember, it is called EIRP. And the total power I am adding, because this is also a gain and this is also a gain, antenna gain. So because gain, I am adding 43 plus 17. So I get total power radiated by this particular antenna is 16 dB. Now let's say there is a mobile here. So I am doing a downlink budget. Okay, downlink a rough budget. So let's say a mobile has to get this power. But the problem here is there is always something called as path loss. Path loss because of reflection, refraction, fading. There are a lot of sort of challenges inside the air interface which will create a loss. Let's take an example. Let's say it has a loss of somewhere around 150 dB. Okay, 150 dB decibels. So 150 decibels is the loss. Now, how much the received power, let's say I put it as RSRP for simpler reason. So RSRP will be 60 minus 150. So how much it will be? Minus 90 dBm. This will be your received strength, signal strength. So typically we need to take a lot of other inputs also. For example, there are cable loss here, there is a VSWR. Those might encounter some losses. There might be some cable here that might encounter some losses. All these things are possible, and then based on that there might be a lot of modeling done. I am just giving you a simple example just to make you understand how the downlink link budget is done. Okay. Now let me go back in the uplink direction now. Okay. So any questions or comments, so that before that I'll because I'm erasing this. If there are no questions, I'll just go back to the uplink later.
Describe once again.
Okay. See, basically what I'm explaining here is, I'm explaining that if an antenna transmits certain power, how do the mobile receives it? So that concept is called link budget. That means this particular link, I am doing a budget, rough budget. So what all assumptions I am making? See, typically, let's say I am putting 20 watt power inside this BTS or E node B. So I am converting that into our dBm scale. So it will be typically 43 dBm. Now this 43 dBm is fed to this particular antenna. Antenna will always typically have a gain because this is the directional antenna. So directional antenna will have a gain, whereas omnidirectional antenna will have 0 dBi gain. So I am assuming that it is having 17 dBi gain. So now 43 dBm plus, because this is also gain and this is also gain, I am adding it up, so it becomes 60 dBm. This is called as EIRP. EIRP because the antenna is radiating this power, and that's why we call it as effective isotropic radiated power. Now, when it goes in air medium, this is air medium. Air medium will always have a path loss. Why? Because whenever we are looking at our voice also, it can travel only certain distance. Why? Because there is a resistance which is provided by the air medium through sort of fading, multi-path, reflection, and all these factors, right? So this path loss, I am just assuming that there is a path loss of 150 dB. Okay. So now my received power will be 60 is the total power minus, because this is a loss. Okay, 60 minus 150, you get typically minus 90 dBm. This will be the typical signal strength what you receive at the mobile end. And this is the range what we are talking in terms of RSRP. Okay, any questions or comments in this? Okay.
Dinesh, TPM, I understand that particular these parameters, but what is the TPI parameter? TPI. What the I means?
I means, see, antenna gain is always with respect to something called dBi. I means isotropic antenna. Always we compare, always we do a relative gain for an antenna with respect to isotropic antenna. Isotropic antenna is an ideal antenna. We don't have this antenna physically. This is just an ideal antenna. And we compare or we do a relative, for example, let's say what we call with respect to 1 millivolt here. Here we make a comparison with respect to the isotropic antenna.
Thank you.
Okay. So always a gain of an antenna will always be dBi. RSRP will always be with respect to 1 millivolt. That's why it is dBm. Sorry, not 1 millivolt, 1 milliwatt. Okay, power is watt. Okay, so let me erase this and I will come back to the uplink budget just to make you understand in uplink how the link budget can be roughly estimated. So let's say from uplink, the difference here is the mobile will typically have a radiated power of somewhere around 1 watt or 2 watt. It is not more than this. Okay. So let me take the higher value here, 2 watt. 2 watt is typically, if you convert it in dBm, it will be 33 dBm. Now this has to be uploaded to where? To the e-node P, right? So now we get the path loss. Let's say the path loss here now in the next instance, let's say it is 100 dB. Okay, I'm just taking an example where it is 100 dB. Now 33 dBm minus 100, how much do you get? Minus 73, right? 73?
67. 67.
Sorry, 67. 67. So minus 67 dBm. Now this is what antenna will receive. Now antenna, I didn't calculate the gain here, right? Because inside a mobile we have something called omnidirectional antenna, which has 0 dBi gain. So I cannot do any addition to this power. So remember this is purely the effective isotropic radiated power from the mobile will be only the power generated by the mobile itself. Antenna will not have a gain. Okay. Now taking the path loss, I get minus 67 dBm. Now let's say I take the same antenna, let's say 17 dBi. Now what do I do? Minus 67 plus 17. How much do I get? $50 dBm, correct?
Minus 50.
So minus 50 dBm. Now the minus 50 dBm, it will come here. This will be the received power by the e-node P. Minus 50 dBm will be our RX sensitivity, or we call it as RSRP, let's say. Typically we don't call this as RSRP because on uplink it is not RSRP. So I will keep it as RX sensitivity. The RX sensitivity in uplink direction will be minus 50 dBm. So these are the factors, typical factors we need to consider when we are doing the uplink budget and downlink budget. There are many other things we need to do whenever we are doing RF planning. But these are the initial parameters which we typically say for assumptions with respect to calculation for uplink and downlink. So there are a lot many models which are been there with the operators. Say they look at, because in urban areas the path loss will be different. In dense urban areas again path loss will be different. In rural areas path loss will be different. In let's say forest area there will be huge path loss maybe because there are a lot of trees. So all these things depends on those topographical conditions. I am just taking some assumptions and doing the calculation for our simpler understanding. Okay. So let me go back to our discussion. So
Vinesh,
Yeah.
one thing, to measure the path loss, is there any device is there?
See, path loss, yes, we have a device, or we have some models called Okumura Hata model. There are some devices also. There are some devices which will actually measure a path loss whenever, let's say, you put a dummy transmitter and a dummy receiver, how much it will receive in each and every area. There are modeling done, and we have certain devices. I'm not sure exactly what those devices are called. But in lab environment also we have some devices. In reality or in real life scenarios also we have those devices. And these devices are little more costlier because these are basically the test and measurement equipment what we buy from lot many vendors. Like there is some solution called Alithia, or let's say Parallel Wire. There are so many companies who are developing these test and measurement equipment which will calculate path loss for each and every areas. That's what I mentioned about dense urban areas, path loss will be different, and we have modeling done for that. And typically what operators will do is, let's say one operator would have done all these sort of trial and error measurements. The other operator might buy that same measurement and do the RF planning based on that.
Okay.
Okay.
Right. Thank you.
Thank you. So let me go to the next one. So typically we see RSRP only being measured. There is also another concept called RSRQ. Okay, RSRQ is reference signal received quality. So basically it is talking about signal quality. Earlier we were measuring signal strength. Here we are measuring signal quality. Typically it is the RSRP over RSSI/N. N is nothing but our typical value what we have with respect to this resource block. So RSRQ also has a range. The range is from -3 to -19. So RSRP had a range of -44 to -144, right?
-140.
-140 dBm. Here it is -3 to -19. For all these values also, there are non-negative values, integer values which have been designated, and the range is from 0 to 34. And remember this is in terms of dB, not dBm. So RSRP is dBm, RSRQ is dB, decibels. Okay, that's the unit of RSRQ. So basically it is telling the quality of that signal. RSRP is telling the signal strength, RSRQ is telling the quality, and these are the values related to that. Typically, we don't use this much. We take this parameter, but we are using RSRP itself for most of our measurements. Okay, but we can do handover or even cell selection, reselection based on these parameters also. But this will be sort of more complex, more stringent when compared to RSRP. Now, what is RSSI? I think RSSI was already there even in 2G and 3G. RSSI is the total power, because RSRP was reference signal only. RSSI becomes the total power. So you can see here, first thing is RSSI is not reported to E node B by the UE. It is just done the calculation. Now, why we calculate RSSI? Because for RSRQ, we require this RSSI value. That's the reason we calculate RSSI. Now, RSSI is measured for entire bandwidth. So this is very important. RSSI is measured for entire bandwidth. RSRP was not measured for entire bandwidth. It is measured only for the reference signal. So RSSI becomes the serving cell power plus noise plus interference power. So if you look at RSSI, it is talking about the complete power what it receives, whether it is from the existing cell, whether it is from the neighboring cell, whether I'm getting some interference, whether I'm getting some noise. So all these things will be calculated by RSSI. So RSSI, you can see here, typically we have this formula with respect to RSRP only, where RSSI is also measured in dBm. And we have some scaling factor with respect to each bandwidth. You can see here for 6, it is minus 18.57. 15, it is minus 22.555. Similarly, for 20 megahertz, it is minus 30.79. So based on this, you can have a sort of RSSI value with considering that I think these values are considered with an assumption that we don't have a neighbor cell. Okay, we don't have a neighbor cell. If we add the neighbor cell, this scaling factor always varies. Okay, so these assumptions what they have made is for a single cell for an entire bandwidth of, let's say if I consider 20 megahertz, the value is minus 30.7. Okay.
Hello, sir. It's Ubad here. Sir, we
Yes.
have discussed about RSRQ, and it ranges from -3 to 90.5.
Correct.
Sir, what will be the best quality? Is it -3 or is it's -3 or minus 90.5?
Yeah, minus 3 is always best quality. Minus 90 is the low quality. Okay. Similar to what we have here, minus 44 is best RSRP. Minus 44, 144 is the low RSRP or the worst RSRP. Okay. And remember this unit, this is very important. I'll just write it down. RSRP is always measured in dBm. RSRQ is dB.
dB.
RSSI is again dBm. Okay. Next is SINR. SINR is nothing but what we have is measured for the signal quality. Unlike RSRQ, it is not defined in 3GPP specification. Okay, but defined by the UE vendor. It is not reported to the network, but UEs typically use it to calculate what? To calculate CQI. So remember this signal to interference noise ratio. So I'll write it down here. Signal is in the numerator and interference and noise is in the denominator. So typically you should have any positive value, then only your SINR will be good. Remember this, I'm not specifying the value because the standard doesn't specify any value. But remember this, if you have a positive value means your signal strength is very good. If you have a negative value means your interference and noise is being overshadowed by your signal. So negative value of SINR means you are in poor RF condition. So this is how you can understand if you are in poor RF condition. SINR positive means you are in good RF condition. Okay. So why is it being used? It is used to calculate the CQI, the channel quality index. So in the subsequent side, you will see the SINR and the corresponding CQI value. So you know what S indicates? S indicates the signal. Okay. The average power measured usable signal, reference signal, and the physical downlink shared channel are mainly involved. So I'll come to this. Basically, this is used for data. I indicates what? Indicates the average power measured on channel interface signals from other cells in the current system. Okay. Basically, it is talking about the neighbor. Okay. And N indicates the background noise, which is related to measurement bandwidths and receiver noise coefficient. Okay. This can be any noise. It can be some thermal noise. It can be some environmental noise. Any noise which is being generated, we term it as N. Interference is basically from the neighboring cells. So you can see here SINR is S divided by interference plus noise. So you can see. Okay. This table will give you an exact picture about what we were talking about, the SINR to CQI mapping. You can see here, first thing is we measure reference signal and SINR that UE will do. UE, based on this SINR, will create the CQI report and send it. So yesterday we saw the CQI value also. Once eNode B understands the CQI value, it generates the MCS scheme based on the CQI value and sends it to UE. Okay. These two things, I'll just explain what it is. If you receive the data, let's say you receive the data and you receive the data properly without any error, okay, without any error, or we call it as, let's say, error free, we have to send an acknowledgement telling that, a positive acknowledgement, okay, we call it as acknowledgement, saying that my data what eNode B has sent is error free. So for that we need to send an ACK. Let's say there are 2-bit error. So UE found out that in the data what eNode B had transmitted, there is a 2-bit error. Now we need to send something called as negative acknowledgement, telling that there is some error, please send the data back or else I will not be able to decode it. This process is called as HARK. Okay, HARK stands for, anyways, we will be going through this tomorrow when we do the protocol stack layer. HARK stands for Hybrid Automatic Request. Okay. Basically, it is telling you if there is a data which I am getting error free, giving an acknowledgement, or we are putting it as negative acknowledgement. So that HARK act to tell you about BLR. BLR means what? Block error rate. To actually give an indication to a eNode B that whether I have received it with an error or without an error. Now, based on this, the next instance, again I need to send CQI because the RF condition keeps on changing. Maybe this will be for 1 millisecond. Next 1 millisecond, I need to again send a CQI to receive the exact data based on the CQI value and the MCS value. Okay. So you can see here, if there is a negative value of SINR, typically we are going with high coding rate and the spectral efficiency will reduce. See, this is the SINR with highest value. You can see what modulation scheme I am using, 64 QAM. What is the code rate? 0.93. That means what? Out of 1 bit, 0.9 bits will be used for data, only 0.1 bit will be used for coding. So very low percentage. So you can see here, spectral efficiency will be 5. So typically in 64 QAM, if I use 64 QAM, how much will be my spectral efficiency without coding? It is 120 Mbps, right? For 20 megahertz, we had calculated this. So 6 out of 6 spectral efficiency, 5 we achieved by having the code rate of 0.93. So you can see the impact. If SINR is high, you will get a higher CQI and you will get a higher order modulation with lower coding rate, and your spectral efficiency also increases. So for every 1 TTI duration, for every 1 millisecond, I need to send this SINR, not SINR report. SINR report will be generated in UE. Corresponding to this, we generate a CQI value and send it to eNode. And eNode B, based on that, will assign an MCS. Any questions or comments? Just checking what is the next. Yeah. Any questions or comments before I move to the next one? Okay. So, are there any questions with respect to? I'm just looking at the chat window. Is there any? Okay, Manas has mentioned. I'm sorry. Are you able to hear my voice now? Okay, any other doubts we have? Okay, fine. So I'll move to the slide. So the next one is about block. Yes.
English, you show me that what are the modulations we are doing in that particular thing. This thing.
This one you're talking about?
Okay, yes, correct. Now,
Okay.
suppose this all the modulations is exist in this particular this LT, or there is a specific RH or antenna that for that it is fixed. How it is?
See, LTE E node B support in downlink. See, I'm talking about in downlink. It supports all modulation speeds: 64 QAM, 16 QAM, and QPSK, all three. In uplink, maybe it depends on what UE category. Typically, we see only QPSK and 16 QAM. 64 QAM we typically don't see in uplink much of implementation. But if you're asking about in the downlink side, yes, it supports all three modulations.
All three modulations. So as per the SNR, value, it will choose the particular modulation, correct?
Particular modulation with respect to particular coding scheme.
Coding scheme.
Yes, that's also very important. It's not only modulation; it is also modulation and code.
Thank you.
Okay, let me go to block error rate. Typically, what the definition of block error rate is the number of blocks what we have got. That means it's a ratio of number of erroneous blocks what we have got to the total number of blocks received in the digital circuit. So it can be divided into two categories. That is initial block error rate. When the E node B sends the data to the UE, UE is unable to decode it. Then it sends a negative acknowledgement. So NAC means that E node will have to retransmit the data, and this NAC is considered as the initial block error rate. Okay. The residual block error rate means that if UE is unable to decode the data even after retransmission, okay, the UE will send another NAC and E node B has to retransmit again. Now, however, there is a limit to this retransmission. The number of retransmission in E node B or in LTE can be only 4, not more than 4. Okay, and the E node B will not retransmit at arc level and consider this as the residual block error. Okay, so the block error rate target is maintained by initial block error, which E node B tries to maintain of 10% for each UE, and the residual block error is supposed to be less than 0.5%. That means the initial error, if it is there, it is ready to take with 10% sort of offsets, whereas it is very stringent with respect to the multiple NACs what we get, because we have only 4 retransmission available in E node B. So it can take only somewhere around 0.5% of the consideration. So that is what is the block error rate is all about. Basically, it is telling about whenever you are looking at the cyclic redundancy tech, the CRC bits, we are looking at some of the errors, and if there is a block of errors, we send it for the first time as a negative acknowledgement. So it's fine to get a negative acknowledgement, and because of the hard process, we do a retransmission. The maximum retransmission possible in LTE standard, according to the standard, is only 4. So after that, we discard the packet. So PCI value, I hope everyone are familiar now. We have 504 unique PCI value. How do we calculate this? The PSS will broadcast, yesterday we discussed this, right? 0, 1 and 2. And SSS will always be from 0 up to 167. So totally it is 168 here. Totally it is 3 here. So 3 multiply 168, totally you get 504. Now for each PCI, how do you calculate? Let's say if I want to calculate for one sector, if I say if it is 3 into, let's say SSS value is somewhere around 30 and PSS value is 2. So you get PCI value as 3 into 30, that is 90. So you get something like this. Okay. So this is how we calculate PCI value. The PCI value will be starting from 0 and it can have 503. This means in LTE, in a cluster, okay, if I will write it in a bigger sheet, let's say cluster means what? A group of cells, right? Group of cells. So group of cells. In a cluster, whatever group of cells what we have, we can have 504 unique cells. That's what it means with respect to the PCI value. Yes, any doubt? Any questions or comments? So this we call it as cluster and this we call it as cell. So we can have 504 unique cells. Similar to in 3G, if you are from 3G background, we had something called 512 scrambling codes. So we could have got 512 unique cells inside a cluster. We could have designed. So typically we don't see all 50 unique cells being designed in reality. We don't see this, but ideally we can design up to 504 unique cell inside a cluster. Okay. In 5G, it is exactly double, 1008. The PCI value in 5G will be 1008. It is exactly double, so we can have 1008 unique cells. Okay. Okay. See, I just go with the minute. So I hope you understand what do you mean by cell and a cluster, right? Okay. So as we understand, let's say this is some group of cells what I am putting, and I put this as a single cluster. Okay. Now here also it is radiating 2300 band. Here also it is radiating 2300 band. Here also it is radiating 2300 band. So all everywhere, let's say I'm putting it as one band. Now, how do I differentiate these cells? To differentiate these cells, I require cell ID, and that is called as PCI, physical cell ID. Okay. In LTE, we have physical cell ID value from 0 to 503, totally 504. So inside a cluster, I can have 504 unique cells. We can design up to 504 unique cell inside a cluster. That's what I meant with respect to this 504 PCI value. Okay. In LTE, this is the one. In 5G, it is all exactly double. And in 3G, we had a similar concept because there also we are using same frequency in all the cells. So to differentiate these cells, we are using something called scrambling codes. Okay, we are using something called scrambling codes because it is a WCDMA technology. There we had 512 scrambling code. That means we can have 512 unique cells inside a cluster.
In 3G, cell quantity was more than this 50.
We can say that yes, standards are developed more than what we say in LTE. You are right, but in reality, we don't see 500 cells being grouped into one cluster. So in reality, you see maybe around 40-50 cells or 30-40 cells. In dense urban conditions, it will be still more lesser. But the standards had specified 512 in 3G, 504 in 4G, and now it is 1008 cells in 5G.
So
Any
just,
other
please Ram, give one question. So the same physical cell ID can be reused in another cluster?
Yes. So inside a cluster, the PCI value should be unique. The other cluster can repeat the same PCI value. That something like correct. Something like how we do frequency reuse in 2G. In 2G, if you remember, we had something called 4x12 cluster or let's say 7 cross 21 cluster, where after 21 cells we used to repeat this. Similar to that, if we design one cluster, the same cluster we can just have a copy of that, and we can have the PCI values repeated there. So 504, what we meant here is unique inside this cluster, but cluster to cluster, it can repeat the same 504 PCI values.
Hello, sir.
Yes.
Dinesh.
Yes, please go ahead.
Dinesh. Yeah, I have one query. Actually, what is the typical distance between the two cells in the urban area?
See, typical distance, it all depends on somewhere around in the band only, right? So bandwidth, see, standard doesn't specify anything with respect to distance, because the band, for example, let's say 2300 band, and if I consider 1800 band, 2300 band will give you lesser coverage, and 1800 band will give you more coverage. So it all depends. So whenever you are doing RF planning, you need to consider lot many inputs, like what band you are using, what bandwidth you are using, and whether you are designing it for, let's say, urban areas, maybe the coverage will be less because there will be densely populated areas. You might see lot many UEs, or let's say in rural areas, you might increase the coverage. So it all depends, and also depends on the power. If you radiate more power, you get more coverage. Let's say radiate less power, it might get less coverage. So it depends on various factors or parameters to do the coverage plan. So typically what we have seen in Geo was, it was on an average in an urban area, it used to give somewhere around 3 to 4 kilometers. And in rural areas, they went up to somewhere around 10 kilometers.
Only for 850 band.
That's for 850 band, not for 2300 band, for 850 band. 2300 band is very less. Yeah, 2300 band is very less. I think 2300 band was around somewhere around 1 or 2 kilometers, not more than that, in dense urban or urban areas.
Sir, during our drive testing for cluster, can we go for a single drive test for different bands? For example, for 850 bands from 420 bands and 2100. That's a single drive test. Or we have to fix the band.
See, as what I remember is, whenever you are going for a drive test for a cluster optimization, typically you are fixing one band. This is what I remember or I see, where they do something called, there is an app inside our mobile called band lock. We need to lock our band to one particular band, and then do the drive test and check the coverage area or capacity, the data rate, the RSRP, all will be with respect to one band only. So only thing what we have to understand is, when we are doing, let's say, optimization point of view, checking the handover, then we might have to check with multiple bands. But when we are doing optimization for a single band, yes, you need to lock a band, particular band, and do the drive test. So typically we see in, let's say, initially we do a drive test with single cell. We used to call it, I don't know what every vendor has its own name, and usually we call it as single cell test, and then we go for cluster test, and usually we do it for a single band, and then we move to multiple band to check the handover, or let's check, we also do a VoLTE test, a data test. All these things are done separately. So I just show you one Excel sheet what I have, talking about all these sort of coverage and MCS scheme, just for your reference. I can share you later once it is done. Just checking whether just a second. Yeah, so I'll just share that. Yeah, I hope you're able to see the screen here.
Yes, sir.
Yeah, you can see basically with respect to 2300 megahertz, taking downlink as somewhere around 2048 kbps
It's
as a
actually the log is very according to this we have to accept the clock or SAFT, na?
that's right. That's right. Okay. So basically, they have given you certain values. For example, in 2300 band, you can see the dense urban and rural areas, what sort of resource block they are being used, what MCS schemes, what are the transport block size, power per resource block, and what you can see here, the antenna gain, what we discussed, typically we are using 17 dBi antenna here, and the receive sensitivity, all other values, the fade margin, the handover margin, and the allowable path loss, the maximum allowable path loss. So all this they have nicely put it across. So I share it to you so that you can use it as a reference how we usually do a calculation for each band also. You can see here for 2300, 1800, 850. I think this is for 850 what they have given. With respect to downlink data, downlink VoLTE, uplink data, and uplink VoLTE. So I can share this so that you can have a look at it with respect to each and everything, what sort of inputs they have considered whenever they are designing. So I shared that in the chat window, so you can have a look at it little later for your reference. So I will just share my slide again. Okay, so any doubts in these LTE parameters, because I'm moving towards a different topic that is nothing but the LTE states. This covers the overall mobility in idle and in the connected mode. So let's have a 10 minutes break now. It's 5:25. So we'll meet at 5:35. Okay, it's not 5:25. It's how much is it? 5:20. So I can see 5:20. We'll meet at 5:30. Okay. So 10 minutes break, and then we'll start with the UEs and the LTE states and mobility. Thank you so much. DCH mode, cell, fetch mode. Okay. So there were totally 5 states which were there in 3G, which had little more complications and little more sort of challenges in having these states for a particular UE. But in 4G, they simplified this and they made only 3 states. Either you are switched off, that means detached.
यही इसी का काम है, बस यही साथ होता है.
Or we are in idle mode, or we are in
तभी तो मैं बोल रहा था आपको, मेरे पास तेरा पहला टाइम होता है.
So it's simple. So mobile can be either switched off, idle, or connected. Now, whenever we are in these particular modes,
ऐसे करो, आप कुछ जुगाड़ना.
That you have your mobile,
आपके हाथ में सब कुछ है, पता है मेरे को. ऐसे मत झूठ बोलो, आपको जाओ मेरे हाथ में.
Or if you are doing some data transaction with the network, I should also understand you are unconnected.
कुछ है.
To do this, we have some states, and that states what we call it as. There are 3 states available. One is
कोई नहीं, एक दो बार और करना ट्राई.
EMM state. EMM stands for EPS Mobility Management. I hope EPS everybody understands now. EPS is LTE, that is the radio network, plus network put together. It is called EPS. Correct. So the EPS Mobility Management, we call it as EMM. Okay. It's very simple.
मेरा तो डिसीजन आपको पता ही है, आपकी मर्जी है भाई, बोलना नहीं बोलना. मैं नहीं बोलता इतना ना, मर्जी आपकी है, करना नहीं करना. नहीं बोलना भाई किसी को. नहीं तो कोई बात भी नहीं करते. पहले तो आप बात नहीं करते, आपने बात करना भी छोड़ दिया.
The first person in the network to know is core network, not the radio network.
वही तो बोल रहा ना.
So
जब तक
specifically it is
मतलब होता है
period.
आदमी का तब तक ही करता है, फिर
Now,
जब मतलब टल जाता है
in
तो
fact, the core network
ऐसे
should
मुंह फेर
know
देता
whether
है
you
फिर
are
धीरे
switched
धीरे।
off or switched on, because if you are
आपने
switched off, I
मतलब
have
नहीं
to buffer
निकाला,
your
मतलब
data.
ये होता है कि एक आस होती है,
Right?
जब आस
So
खत्म हो
the
जाती है ना तो आदमी
EMM
धीरे धीरे जब पीछा छुड़ाता है।
deregistered is a parameter which
आदमी
is
का
taken
नेचर
care
होता
by
है
the
ऐसा है,
core network. That means you are switched
सबका नहीं
off.
होता, आदमी का होता ही होता
Let's
है।
say you register
छोड़ो
now.
क्या
That
बोलना
means
किसी
you
को,
come to idle mode. Okay.
अपनी
When you
अपनी
come to
किस्मत है।
idle mode, there is one more thing which is
आज
called
मैं
as
आपके हाथ में, कल मेरे हाथ में
ECM.
होगा।
ECM means what? EPS connection management. Okay.
सुख दुख
So
चलता
EMM
रहता
deregistered means you are switched off your phone.
है।
EMM
मैडम
registered
अगले
means you are
जन्म में
switched on
मिलेंगे
your phone. Okay. You are switched on your phone. That means you are attached with the network.
इस
You are
जन्म में नहीं
attached with the
मिलेगा।
network. Now, once you attach with the network, then you have only two states. Either you should be in idle mode or you are in connected mode. This phenomenon is called
मैं
ECM.
ऐसा बंदा नहीं हूँ कि
ECM
भी मैं
stands
हर
for
जगह ट्राई करता रहूँ,
EPS
जिसको एक
connection
बार बोल दिया
management.
तो बोल दिया,
So
नहीं
you are in
बोला तो
idle mode
अपनी
or in
मर्जी है उसकी,
connected.
जरूरी नहीं है
Now,
किसी को।
this is also
मेरा
at the
नहीं
core
है लारे
network side.
लगाने वाला काम की भी मैं
So
हर
core
किसी को ऐसा
network will
बोलता
take
फिरूँ कि
care
हाँ
of
यार
this
तू भी सही है,
and also this.
अपना नहीं ऐसा भाई।
Now, what does the radio network do? At the radio network, we have a
किसी ने
layer
करना होगा,
called
ठीक है, नहीं
RRC.
करना,
Anyways,
समझना
we are
होगा,
going
किसी ने
to
समझे
discuss
है,
this
नहीं समझ
tomorrow.
रहा मत
Just
समझो,
to allude and talk about
जो
this,
बोलना है किसी को।
RRC stands for Radio Resource
हाँ
Controller, which takes care of
करो आप
complete
रेस्ट।
radio resource management of your network. It is like we usually call this as L3 layer. L3 is nothing but creating the connection management within the radio network. So when you are in idle mode here, RRC will also be in idle mode, let's say. That means you are connected with the radio network also, and you are connected with the core network also. Now, once you come to, let's say, connected mode, that means what? Now you are doing some data transaction. Let's say you are doing a VoLTE call. Now the radio network will put you under RRC connected state. Okay. So RRC connected state means what? You are doing some serious data transaction within the network. Let's say you drop your VoLTE call. Now the network will push you in RRC idle mode. Okay. So these are the three different sort of entities which are there inside the mobile, inside the network, wherein EMM deregistered means you are switched off or detached with the network. Registered means you are switched on. Once you switch on, you are under two different modes, that is idle or connected. In the core network, it will be considered as ECM idle when you are in idle mode, and connected means you are ECM connected. In the radio network, this will be RRC idle or you are RRC connected. Okay. Now, when you are in idle mode, your location is being tracked based on something called as tracking area. So who takes care of this? Which entity? MME. If you remember, we had discussed this earlier. MME, Mobility Management Entity inside the EPC, the core network, will take care of tracking area. So tracking area, as I discussed, is not a single cell. It will be a group of cells, and it is not a cluster also. It is a group of cells, and this group of cells is designed purely based on the topographical condition of that area. Okay. So that's about the tracking area. So a UE position, whenever you are in idle mode, will be purely based on tracking area. Okay. And when you are in connected mode, the UE position will be purely based on cell area. Okay. So exactly which cell you are in, that is being tracked whenever you are in connected mode, because we need to do handover. Okay. So tracking area is being taken care by MME, handover is taken care by E-road. So this is called as, this particular thing is called as idle mode mobility, and this is called as connected mode mobility. Okay, any questions or comments before I go to the next slide? Okay, so I'll move to the next slide. This will give you an idea about what we talk about this registration, connection, and idle mode. See, you can see the first instance here. This is the first instance where EMM is registered. That means what? We have switched on our phone. ECM is connected. RRC is connected. What does this mean? That means you are doing some, let's say, I'll take one example so that we can understand. Either you're doing a VoLTE call or let's say you're doing a video call through your operator network. So this is very important. VoLTE or a video call through your operator network. Okay. Now, we discussed this in our earlier stage that from UE, we need to have an end-to-end flow, end-to-end connection. So this is P gateway and this is UE. So you can see here, our main aim is to establish one bearer connection, which has to be this EPS bearer. Correct? But can we have a physical connection? No, it is a logical connection. So how do we get this logical connection? We have to get a connection between UE and E node B, which is called as RRC connection. Since it is a data, it is called data radio bearer. Typically, it is called radio bearer. Since we are doing a data transaction, it is called data radio bearer. Now, whenever we are doing a data transaction, is there any signaling which is required? Let's say you're doing a VoLTE call from UE to, let's say, one UE to another UE. Do you require signaling? Yes, we require signaling because if we are doing a handover from one E node B to another E node B, this is called as signaling, or this is called as control information. So this control information is taken care by RRC connection. So RRC connection, that is control plane, will take care of your handover, and radio bearer will take care of your VoLTE connection. Okay. Now, next part is, this is about till the E node B. What about this? So here we have S1 bearer. In S1 bearer, this is taking care of signaling. This is taking care of user plane. So S1 signaling will have S1 C bearer, which is taken care by MME control plane, and S1 U bearer. Totally it is called S1 signaling. Okay. And we have this tunneling protocol. Typically this was used in GPRS also, the same tunneling protocol we are using, which is called GPRS tunneling protocol for control plane. Similarly, for your data, we have an S1 bearer which is connected to S gateway, S5 bearer which is connected to P gateway. So this means an EPS bearer is a combination of your radio bearer, S1 bearer, and S5 bearer. Okay, and this state is called EMM registered, ECM connected, RRC connected. That means we are doing some serious transaction with the network. Okay, whether it is VoLTE call, or let's say, I'm just taking an example of VoLTE call, it can be any other internet-based transactions also. Let's say you're doing a WhatsApp transaction, you're uploading a video, you're downloading a video, all this becomes a data transaction. Now, let's look at the second instance where we are not doing any data transaction. That means we have registered with the network. We are in idle state and also RRC idle. So what does it mean? We have registered with the network means this bearer is alive, this also bearer is alive, this is also alive. All this will not get activated because we are not doing any data transaction. The moment we do the data transaction, then MME will track the UE based on tracking area. It will do the paging, because paging is required to do the incoming notification. Once the paging is successful, UE will give an acknowledgement and then we will get all this connection back, so that we get into the connected. So we don't call it as dedicated mode, we call it as connected mode here. Unlike in 2G and 3G, it was called as dedicated mode there. In fact, in 3G also at HSPA level, we used to call it as connected mode. But before that, we used to call it as dedicated mode because it was purely on the circuit switch aspect. Now it is because of the packet switch behavior, we call it as connected. Any questions or comments before I go to the next slide? So here you can see the EMM, that is EPS, mobility management, bearer and signaling.
This is a virtual world and does not represent real life.
So let me go to the next slide. Okay. Next one is about handover, what we have in LTE. Okay. So purely handover means what? Handover will be only taken care by eNodeB. Now, in this, just before going to handover, I just want to give you some perspective with respect to handover. See, handover means, let's say this is eNodeB. Typically, we call this as, if I'm connected with this eNodeB, let's say, we usually call this as source eNodeB. And let's say, suddenly, if at one moment of time, there is one more eNodeB here. Okay, let's say I put it as eNodeB2 and this as eNodeB1. This might be, we call it as neighbor eNode. Okay, or we also call it as target eNode. Okay, source eNodeB or neighbor eNodeB, or it is also called as target eNode. Now, this is, let's say this is one area, and we have, typically we have an overlapping condition here. Okay, and let's say we have an interface here which is called X2 interface, and remember this typically will be a logical interface. It might be a physical interface also. This is up to operator, but typically implementation wise we see a logical interface itself. Now, this eNodeB and this eNodeB might be under 1 MME. Let's take an example. Let's say it is under 1 MME, which is an S1 interface here. So whenever there is a handover, that means if a mobile moves from this eNodeB to this eNodeB, whenever the handover takes place, this will be typically an X2 based handover. Okay, this will be typically an X2 based handover. Let's take an example, let's take an instance where if I don't have this X2 interface at all. Okay, so we don't have X2 interface, and we have this coverage area, there is this coverage area also, and let's say there is no X2 interface, but both are connected through this S1 interface. Now, if we don't have an X2 interface, then we go through another handover mechanism which is called S1 based handover. Usually we don't see this much, but the standards define both sides of handover, which is X2 based also and S1 based also. Okay, so remember we might use these terms called source eNodeB or neighbor eNodeB or neighbor eNodeB, or also called as target eNodeB. So remember, whenever we mention all these things, it is talking about these handover parameters itself. And we might have an X2 based handover also, or an S1 based handover also. Now, on what basis this handover takes place, I'll go through the slides. And if you have any questions or comments, you can please raise your hand based on that we can address those things as well. Now, handover, whenever we say handover in an air medium, it typically is taken care by this particular entity, which is called as RRC. Okay, so how do we do this? UE does a measurement report and sends to something called serving eNodeB. Okay, source eNodeB or serving eNodeB are one and the same. So serving eNodeB will receive this measurement, and based on certain parameters, so we look at what are those parameters, and based on that we will do the handover to the particular UE. So you can see here informs about set of eNode Bs to be monitored while moving through the network. The serving eNode B also informs about criteria to be used for measuring and reporting channel strength and quality. So here we are taking example with respect to RSRP, and typically we see a lot of implementation with respect to RSRP itself. So we'll take that into consideration and we'll discuss this.
Watch out.
So what are the things which I need to measure? So first thing is what I need to measure from UE, which one I have to measure, how I have to measure, and when I have to measure. So what are those things which I need to measure to do a successful handover? We'll see that. So these are the things which a UE is supposed to do. So we'll see here. First thing is what I need to measure. We need to measure intra or inter-frequency channel. That means 2300 band is there. If I want to move to 1800 band, this becomes inter-frequency handover, right? But there are chances that there is an 850 band here. There is one more 850 band on the cell edge overlapping area. So this becomes intra-frequency. Or sometimes, let's say, inside the cell also, if you are changing. See, let's say this is one sector, this is one more sector, and this is one more sector. Let's say we are in 2300 coverage area. We move from this sector to this sector. This also become intra-frequency handover. Okay. Next, which one to hand over? That means we have listed eNode Bs. Typically, sometimes we see this, but I don't see this as an implementation. But standards say you can backlist some of the eNode Bs. That means what are the listed neighboring eNode Bs that we need to measure. Okay, how we need to measure? Reference power level. That is basically talking about RSRP. Okay, when during the measurement gaps, that means whenever you are not doing any transaction in your connected mode, that gap we need to do the measurement. When to measure or when to report, that is periodically or event triggered. Typically in LTE we are going with event triggered or event based handover. Periodically or periodic based handover we are doing it in 2G. Okay, here we are going with event based handover. So what it basically means is, in 2G, we were sending our report every 480 milliseconds. Whether your signal conditions are good or bad, whatever it is, it used to send this report every 480 milliseconds. That means in a second, 2 times. So in this, the drawback was, even though if my conditions are good also, UE is sending its report to mobile, which is, UE is sending its report to eNode B, which is unnecessary. Event-based handover means eNode B will give you certain instances that when the threshold of, let's say, one cell drops or another cell increases. So all the thresholds are already defined, and the event is triggered and reported only when these values are going beyond those threshold values. So that's the benefit here is only when your signal strength is reducing, let's say the event gets triggered, and when the event gets triggered, UE has an authority to report it to eNode B so that eNode B can take the decision on the handover. So as I mentioned earlier, the assistance is given by the mobile. That means UE will measure all the reports and sends it to eNode B. eNode B has authority to do the handover or not. Okay. Okay. So let's take one example here with respect to measurement of UE. See, we are taking an example with respect to 20 megahertz. We typically see the transmission power is 20 watt. We are converting it into 20,000 milliwatt. Now, total number of subcarriers in 20 megahertz is 1200, that is 100 resource block. Now power per each resource block, how much do you get? You just take a division of total power divided by number of subcarriers. So per subcarrier, the total power, per subcarrier, the power will be 42 milliwatt. Okay, per subcarrier. Okay, that means the transmitted power in the reference signal. So you remember the reference signal, right? In the reference signal is, take an example, 42 milliwatt. Now this 42 milliwatt is equal to how much dBm? 16 dBm. Okay. Now take this example, what we did the link budget, right? So 16 dBm is your transmitted power plus the antenna gain. We are taking an example as 10 dBi antenna. So we add that 10 here. Let's say cable loss of minus 3 dB. So we are reducing it. Path loss of 116. So how much do you get? 23 minus 116. This is how a mobile calculates, that is RSRPs minus 97 dBm. So in the earlier example, if you remember, the link budget I had not taken with respect to each reference signal, right? Or each RE. Here, they are going at this level so that we can clearly understand that one RE will give you somewhere around 42 milliwatt, which is one reference signal power, which is equal to 16 dBm. And we are looking at some of the other parameters which affects our link budget, that is antenna gain, cable loss, and path loss. So we are assuming some values and putting it so that you can clearly understand what is the received power which you get at the mobile network. Okay, so typically based on this, we can do some measurement. We can take some offset and threshold values, which are also defined by the implementers. That means standard doesn't say what sort of standard clearly defines what sort of events we have got in LTE, but it doesn't say what sort of threshold values needs to be kept to do the successful handover. So that is up to let's say vendors or operators to design those values and put those values across for handover purpose. Okay. So let's look at what are the different sort of events what we have got in LTE. These are intra and inter-frequency based handover. That means if you see A, that means it is within the LTE network. There is one more thing which is called IRAT handover. IRAT handover means it is moving from 4G to, let's say, 3G or 2G. Anything is possible. This is also defined, and this usually we call it as event B1 or B2. Okay. We typically don't do periodic reporting. That means it will not specify any time. Basically, we are going with event-based handover itself. IRAT stands for Inter Radio Access Technology. Okay, Inter Radio Access Technology. So let me come to the intra and inter-frequency handover. See, let me start with this first, because this is the one which we usually typically see, that is event A3, where the neighboring LT cell rises above the serving cell plus offset. What does this mean? I'll just put it under a graph so that you can understand these things better. Let's say this is the time axis and this is the RSRP level which we are measuring. Let's say this is the first E node B. This is E node B1, which is the serving E node B. Okay. Let's say this is the E node B2, where we need to do a handover. This is the target E node B or the neighbor E node B. So at one point of time, usually we see an overlap. Let's say this is the overlapping one, and then this signal strength increases. So what I am trying to say here is, let's say a mobile is here. Okay. let's say I am keeping an offset value here. Offset means this is where we have an offset value. These values are not specified by standard, so that's why I'm just giving you an example how we can decide about the handover. So let's say the mobile is here, he is moving in, let's say, a cell edge area, and somewhere he reaches here where the coverage from both the sides is saved. So now also the event is not triggered. See, I'm talking about which event? Event A3, where neighboring LTE cell rises above serving cell. That means still our neighboring cell has not increased, right? So this is target A node B. So mobile is here. Mobile is slowly moving here, let's say, and it comes here. Let's say it comes here where we have set some offset. We have set some offset. Somewhere here, we get the A3 event which will get triggered. Okay, it will get triggered. Now what will mobile do? Mobile will start sending report to the source E node B, telling that my signal strength coming from source E node B is reducing and signal strength of target E node B is increasing. So it will send this report to E node B. Which E node B? The source E node. Okay. And the source E node B will send this, the UE will keep on sending this report till the handover will take place or the event A3 gets diminished. This might also be a possibility, right? Let's say the UE is here, suddenly he might go back in the same area also. So in that case, we need not do a handover itself because he is again gone back to source E node B where the RSRP value is much better than the target E node. Okay. So this is the meaning of A3 event, which means that the source E node B or the neighbor, what we call it as the neighboring E node B or the target E node B's threshold will go beyond the offset, which will trigger A3 event and it will do a handover. Okay. So we have spoken about now about A3. Any questions so far? I'm talking about A3 because I'll come to A1 because A3 is the typical predominantly used one. So that's why I'm talking about A3. Okay. Now the next thing is, let's say, what is A2? A2 is serving cell falls below the threshold. That means my RSRP value of the serving cell is going beyond the threshold. Whatever threshold I've set here, it is going beyond the threshold. Now what should we do? Whenever an A2 event is triggered, the LTE node B either has to give the list of cells, list of neighboring cells, which are falling under intra-frequency, inter-frequency, or there might be a possibility of this also, of IRAT frequencies. So what it will do, if an event A2 is triggered, E node B will give a list of frequencies in the neighboring cell, which will give you the threshold values of intra, inter, and also the IRAT. And then it will go to A5. Now what does A5 say? Remember this, the serving cell falls below threshold 1, neighboring LT cell rises above threshold 2. So this is little more sort of giving you more sort of instruction when compared to A3 event. In A3 event, the moment you are going beyond the offset, you are announcing that the A3 has been triggered. But look at A5, how it takes place. I'll just sketch it so that we can understand things better. Same time we are taking here, let's say this is the RSRP value, okay? Let's say this is the source E node B, what we have. This is the neighbor E node B, what we have got. So what we do, for source E node B, let's say I keep a threshold here called threshold 1. And the target E node B, or let's say, sorry, this is target E node B, threshold 1, threshold 2, and source E node B, let's say I keep a threshold 1 here. Okay, so source E node B threshold is this, target E node B threshold is this. Okay, so now what happens? So whenever the mobile is moving here, that is threshold 1, right? It will try to tell that I have already gone beyond my threshold 1 of serving E node B. Okay, and I am somewhere reaching at the range of threshold 2, that is target E node B's value also I am reaching. And at this point of time, we have something called event A5 which is being triggered. So the difference is, in event A2, there was no threshold which was defined. There was only offset value based on that event A2 was being triggered, A3, sorry. And event A5 is, the E node B will define all the thresholds with respect to the source E node B as well as destination or the neighboring E node B, and the event A5 will be triggered. Now, also remember this, event A5, once it is triggered, UE will inform this to E node B till handover success takes place, or event A5 gets completely diminished. Okay, so either of these conditions should be there for your event A5 to get stopped. So that's the one with respect to event A5. Any questions or comments before I move to other events? So same thing with respect to event A1, what it means is, serving cell rises above the threshold. That means if you are in certain areas where event A1, that means your serving cell itself is going above the threshold, it doesn't require any intra or interfrequency. That's what it means with respect to A1. So A1 is typically a simple format where you are in the source E node B and just informing the source E node B that you are within that threshold. Then only it gets triggered. Typically, we will see more of A3 and A5. And in case if you have an inter-radio access technology handover, then you will get into event B2, where serving cell becomes worse than the actual threshold of 1, and the neighboring 3G or 2G frequency will have a better threshold than the serving threshold. Yes.
Can we define the same way to threshold? Threshold is minus 144. This RSRP.
Correct.
Here we
Marked a location.
link this threshold force.
Yeah. You see, with respect to how you define inside the network is purely up to RF implementers only. And you can define whatever the range value is there, within that, whatever threshold you want to design, you can define it. But whenever we are defining, this is not one instance we need to check. We need to keep on monitoring the network, because whenever UE sends this data, we need to look at the log files that sometimes handover success rate might be very less whenever we are checking this data, right? So we need to look at or diagnose these problems and look at what threshold values we have set, and we might change those threshold values.
Get in the car.
Minus 144 is not threshold.
No, minus 144 will be very less sort of value, right? So we will not go till that value to define RSRP threshold value. It will be somewhere in the range of minus 100 only. Minus 144 will be very low coverage area where maybe UE will also not have the room to take that handover sort of capability decision, right? So it will be way beyond, somewhere around in the average range of -100 or -110. And that threshold might be set.
Usually, doesn't have
Can you repeat the question, please? I'm not able to hear your voice properly.
X2 interface is down.
Okay, I will come to that. If I'll come to that. I just if you want, I can just jump wherever it is. Yeah, we have the next slide. I'll come to that so that you can address. See, what if you are asking what if you don't have X2 X2 connection, correct?
X2
Or
interface
X2, yeah. If you're telling X2 interface is down.
X2 is there, but some due to some technical issue or any other issue is not working or it's down.
If that is the case, it will go like this. You can see here, it will do a handover with using S1 based, using the S1 based handover. So
both the interface will be there.
yeah, both the interface will be there, but typically X2 is much faster when compared to S1. And usually operators or implementers will never want to go with S1 because it has its own challenges because of the delay. So usually go with X2. And as you pointed out, in case if the X2 is down, this will typically not happen inside the network, but taking some hypothetical condition, if this is down, it will obviously go through S1. Okay, any other questions or comments before I start with this X2 and S1 handover? Okay, so let's look at what is X2 and S1 based handover here. You can see here, this is X2 connection. That means this is the X2 connection, but E node B to E node B2 to E node B3, we don't have X2. So if a mobile, you can see here, this mobile is going from here to here. This is X2 based handover. You can clearly see here, it is X2 based handover. But if you're going from here to here, what is this called? This is called as S1 based handover. Okay. So now you can see here what are the changes we can see in the control plane and the user plane whenever we are doing a handover. Here there will be an RRC connection, S1 connection, and these are the S11 GTP protocols, tunneling protocols, what we have in between MME, S gateway, and P gateway. Okay. When you are moving, the RRC connection will go to, you can see here, you can go from RRC connection. That means there is a change in RRC connection because there is a change in E node B. But the S1 signaling remains, connection with respect to MME remains same. So there will be, if you have the same MME, it will be same connection, or it might go through a different pooling. And then you might go through another RRC connection if you are going to one more E node B, and the signaling will also vary based on that. Now, this is with respect to control plane. So this is where the important thing lies with respect to what we discussed right now, right? The event A2, event A3, all these are happening in control plane. Once this trigger takes place, next thing is we need to transfer the data, because let's say we are doing transaction with this E node B. At next instance, we might have to do transaction with this E node B. That means the tunneling has to take place between this E node B to this E node B via X2 interface. That is nothing but our data radio bearer. So earlier it was with let's say one E node B, then it might move to another E node B, and then it will go to the final destination or the targeting. Okay, and similar to that, we will have an S1 bearer for between E node B to S gateway to P gateway, because this is mainly on the connected node. So it will be taking care of S1U and S1. Any questions or comments? Yeah, I just want to see a chat window if anyone has put across any questions. Okay, fine. So let me move to the next bit of slides. I think I'll quickly summarize whatever we discussed today. We discussed on RSRP. RSRP stands for reference signal received power. It has a value range from -44 to -140 dBm. The unit is dBm, and -44 means you are in good RF condition, and -140 means you are in poor RF condition. Okay, and it is reference signal received power. I can hear some voice. Can you mute your mic, please?
একদম স্টার্টিংত কোনো হয় তাৰ সেকেন্ড টাইম ওচৰতে লৈছিলো তাৰে আপুনি আহিছিল নেকি মৰ্নিঙত
So can you mute your mic, please? Who is that? I cannot see who is that who is speaking here.
হা 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 হয় তেতিয়া ওচৰ তাৰ কাষতে পানী মানে আমাৰ পানী চেণ্ডেল বেগত ভৰাই কিবা কৰি অফিচ যাব পাৰিছো আৰু
Excuse me, can you mute your mic? I'm able to hear you.
Shizu, what is the same? মই এতিয়া কি এইফালে ভিতৰত
Yeah, I have muted him. Yeah, thank you. Okay, so RSRP is fine. RSRQ, basically it is talking about quality. The unit used is dB. Okay, one more thing is it has a non-negative integer value from 0 to 97 for each and every RSRP values. RSRQ is measured in terms of dB, and we have a value from -3 to -19.5, -3 being good and -90 being in poor RF condition. And SINR, signal to interference and noise ratio, basically standard doesn't define anything on this. UE measures this purely for creating the CQI value. Block error rate purely for checking the error coded bits and to send the acknowledgement or negative acknowledgement through the mechanism called as HARP. And this HARP is typically done at MAC layer, so we'll look through this tomorrow in detail. So these are the things which we have discussed with respect to the LTE measurement parameters. PCI value, as we discussed yesterday also, PSS we have 3 groupings, 0, 1, 2, and SSS we have 0 to 168. So totally we have 504 PCI value. So we can have 504 unique value inside a cluster. So between 2 different clusters, we can repeat these PCI value. Cell selection, reselection happens in which mode? RRC idle mode. And handover takes place in RRC connected mode. And remember this, we change whenever we do handover in LTE, it is called as hard handover. Okay, hard handover. Handover in LTE can be X2 based or S1 based. Okay, handover in LTE is called as hard handover. Fine. So any questions or comments before I go to quiz? Okay, so let me go to quiz. Yeah, so the unit used to measure RSRP is
dBm.
dBm. Okay, very good. dBm. Okay, next. 30 dBm equals how much watt?
9 watt.
No.
16.
No.
Actually, mobile cannot transmit this much power.
Correct. So how much is it?
Forget.
Okay, I will just write it so that
2 watt. 2 watt. It's 2 watt.
Approximately.
33 dBm is 2 watt. 30 dBm is 1 watt. Okay. So how do we calculate this? dB means 10 log to the base 10 P1 by P2. Okay. It can be output power by input power, or we call it as P1 by P2. dBm means 10 log to the base 10. The input power is P1. Output power, or it is always with respect to 1 milliwatt. So this P1, now I replace it with 1 watt. So milli comes on top, let's say, so it becomes 10 log to the base 10 of 1000. So how much do you get? 10 log of 1000 is 10 into 3. That is 30 dB. Okay. I hope you got this. Do you want me to repeat it? Anyone? Okay. One more important thing is 30 dBm. If you add plus 3 dB. Okay, remember this, dBm and dBm cannot be added. Always
be double.
Correct. It will always be double. So 2 watt. So 33 dBm is 2 watt. If I add one more plus 3, it will be 4 watt. Okay. 30 dBm minus, let's say 3 dB. Answer is what? 0.5 watt. Or I can say 27 dBm. So always remember this value, because if you remember this value, you can remember, let's say if I say any other value, you just need to add plus 3 and you can double the power. So 36 is 4 watt, 39 dBm or 39 dBm becomes 8 watt, so on and so on. Okay. So the answer for this is 1 watt.
So 0 dBm is equivalent to 1 milliwatt.
Yes, 0 dBm will be 1 milliwatt. Correct.
Okay.
Okay. So let me move to next question here. The unit used to measure RSRQ is
dBi.
dB.
dB, not dBi. dBi is dB. Okay. So the answer is dB. So I'll write it here. RSRQ is dB. dBi is for antenna. So dBi stands for isotropic antenna.
Isotropics means omnidirectional, means it is all surround the, if it is transmit all direction, all 360 direction, right?
Yes, you can say that, but isotropic is an ideal antenna. Omnidirectional antenna is there inside your mobile. Typically, omnidirectional antenna will also not have any gain. It is a 0 dBi gain. Whereas the antenna what we use at the site, right, inside E-Node B, that will have typically 17 to 19 dBi. And if you look at microwave antenna, it will have very higher gain when compared to our cellular antennas.
Because actually in the reflector in the microwave antenna, what it is, actually it is throw omnidirectionally, but it reflects back to a direction.
Basically it is a high beam antenna. See, microwave antenna is a high beam antenna.
High beam antenna.
So because of high beam antenna, you get high gain.
Yes.
Typically, if we look at inside our cellular network, it will be 65-degree beam width. So that's why your gain will not be as high as microwave antennas.
Yes. Microwave is very narrow beam.
Yeah, very narrow. Correct.
So that all power of omnidirectional converted to something 5 degree or 10 degree, like between like that. So it is very dense. The wave very
yes,
dense.
it will be typically the beam width will be somewhere around 10 degree. gives you a high gain. It will be very high gain when compared to whatever we see at the cellular side, right?
Yes, thank you.
Okay, the next one, SSS value ranges from dash to dash.
Zero to 167.
Correct. 0 to 167, totally 168. You can see here. Okay. Okay, the last question here. Okay, can you calculate and let me know 46 dBm minus 2 dBm? How much is it in watts? So you have understood the question, 46 dBm minus 2 dBm, but I don't want it in watt. Sorry, dBm, I want it in watts.
26 watt?
Sorry?
dBm. It will come around 20 watt, 20.6.
Correct. So you get somewhere around 20 watt, but I think I've done a typo error here. Let's look at easier way. Let's say if I consider 33 dBm, how much will be the answer? Because I think you will not get the perfect answer for this. If I consider 46 dBm minus 33 dBm, what might be the answer for this?
Which one?
See, I will write that question for you again. So, just to make you understand, let's say 46 dBm minus 33 dBm. What will be the answer in watts? Can you calculate and let me know?
Yes, wait, please. 3, 6.
सात 33 7 40 16 32 watt.
20 micro.
Not 20 microwatt. It will come in watt only, not micro. How much is 46 dBm in watt?
32 watt.
Is it so? 32 watt? See, 43 dBm is 20 watt. So plus 3 I have added, that is 46 dBm. So it becomes 40 watt. So 46 dBm is 40 watt. Okay? Minus 33 dBm is, as just now we calculated, is 2 watt. So the answer is 38 watt.
But if you same thing, if dBm to dBm you subtract 46 minus 33, it is coming to 13 dBm.
Okay, that's why I took this purposely I took this valuation, because we cannot subtract dBm with dBm. Okay, remember this. We cannot subtract dBm with dBm. We will not get the exact value. Okay, it will always be, you have to convert this in watt, which will be 40 watt. You have to convert this in watt, this will be 2 watt, and this is what you get. If you directly subtract, you will not get the exact value. You will in fact get, for example, if you see 43 minus 33, you get 10 dBm. 10 dBm is not the value of 38 watt. That is because this is a relative value and this is a relative value, that's why you cannot minus. 43, you, sorry, what is that?
How are you converting 43 dBm into 40 watt and 33 dBm into 2 watt?
Sorry, please come again. What is that?
You are converting 43 dBm in 20 watt.
Yeah, how do you are asking how do you get 42 dBm as 20 watt?
Yeah.
See, See 30 dBm, do you understand this 30 dBm? Just now we discussed it is 1 watt. How do we get you understood, right?
Okay.
Now we understood that the moment we add 3 dB, the power will get doubled. That means 33 dBm. If we add plus 3 dB, we cannot do plus 3 dBm, okay? dBm cannot be added with dBm. Always dBm can be added with dB only. So if I add plus 3, it will be 33 dBm. Answer is 2 watt. Just remember, next is 36 dBm. Answer is 4 watt. Next is 39 dBm. Answer is 8 watt. Next is 42 dBm, which is 16 watt. Now next is 45 dBm, which is somewhere around 32 watt. Now this is in between, so I'm just adding 1 dB, which will come up to 20 watt, which is 43 dBm. Why I'm saying this? Because typically we in our wireless communication for E node B, this is the transmitted power, which you get a calculation with respect to 43 dBm. So what I did was, I remember this 43 dBm is 20 watt. 46 dBm means plus 3 dB, right? So I just double the power, which is 40 watt. Okay. And then 33 dBm also, we know the value, it is 2 watt. So what we do? 40 minus 2. I have to do a normal calculation. 40 minus 2, that is 38 watt.
Vignesh,
Yes.
If it is watt, it is watt, dBm is milliwatt, right? Reference value is milliwatt for dBm, right?
What is that? Can you repeat?
Reference value for when I calculate dBm reference value is milliwatt, right? Like
correct.
Right?
Reference is milliwatt. Correct.
My confusion was when we calculate suppose we here maximum people is transmission there, means optical transmission. When we calculate the fiber loss, then we just subtract from TX power to RX power. This is the fiber loss. Fiber loss measured by dB.
Correct. Okay.
Actually, as a dB is the difference of 2 dBm. So if I calculate the loss of a fiber by subtracting 2 dBm, and it is, as I know that it is perfect. But here, if I see you already show us that it is actually not correct. If we subtracting 2
correct.
dB.
Actually, dBm minus dBm we cannot do. You can just check that, right? See, you can see, I'll just calculate here only. Let's say 33 dBm minus 30 dBm. What is the value?
3 dBm.
3 dBm, correct? That's what you say.
3
But
dB. When you subtract dBm to dBm, then it will be dB.
Correct. So this is 3 dB. So what you mentioned is correct. What I'm trying to say is, my question there was 46 dBm minus 33 dBm. What is the value in watts? I want it in watts. So that's why now I'm not asking you 46 minus 33 to put it in dB or watt. We want it in watts. So that's why I need to convert this in power, normal power scale. This also in power scale, so that I get the value in watts. That's what the question is. According to the question, I am putting this.
Okay, that I understand. If we subtract this, it coming to dB. If 3 dB we convert it to watt, then it will not.
It will not come. That's what I am trying to say. That dBm and dBm like this, if you subtract, you will not get it in watts. You will get it in dBm maybe, right? Or dB. In fact, it is not dBm, it is dB. I should actually mention the value is 13 dB. Correct? I should not mention it as dBm. I should mention it as 13 dB. But the question here was, it was in watts.
13 dB to what?
13 dB will be the loss. That's what it means. 46 dBm minus 33 dBm means 13 dB is the loss.
Okay.
Okay, 13 dB will be the loss. The context here was, I am asking in terms of watts. That's why we need to convert this in power. We need to convert this in power. Then only you get this. So the question here, someone asked me why 46 dBm you are putting it as 40 watt. That is because I remember that 43 dBm, which is typically used in our E-node B, which we call it as 20 watt. I just doubled it because plus 3 dB it is 40 watt. And 33 dBm is the value which is there inside your UE, which is 2 watt. So minus 2, we got 38 watt. That's how I arrive at this solution. Okay. Any other questions? Okay, so any other questions or comments before we end our session today? Okay, if there are no questions.
Answer
Yeah.
sheet.
Sorry?
The quiz sheet.
Can you please repeat? You want the quiz sheet, is it? You mean? Okay, if there are no questions or comments, we will wind up for today. We'll sign off. So thank you for your patient listening. So we will meet tomorrow at the same time at 4 p.m.